So this is beginning of 6.1, chapter 6, understanding the two main concepts of calculus. Calculus answers two fundamental questions regarding curves. In its simplest form, in high school math, it answers what is the instantaneous rate of change, blah 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 blah, whatever. And the main thing here is instantaneous rate of change when it's not a line, when it's a curve. So, like here, at any point, if I knew what the function is, I can just take the derivative of the function and evaluate it at this point, x equal -1, and I'll get exactly what the rate of change is at this point. That I wouldn't just assume is some negative slope, no? So that's what we did first semester. And then what did we do to find the exact rate of change here? We'll just get the function, if it's f of x, take the derivative of f of x and evaluate it there. So that would be, most of the times it's a position function, but it doesn't have to be a position. It could be, that's what the problem is sometimes when this is not given, because it could also be a velocity, no? You could say that f of x is equal to velocity. So if this is a velocity, then take the derivative of this to get the acceleration. So this is that it is, let's say for right now, is that it is a position function, but okay, yeah, f of x is a position, so take the derivative and find the velocity. In this case, we apply the constant of the derivative to find the instantaneous rate of change at any point, no? All right, second semester, starting now, is that the other question is, for that same curve, another question is, what is the area under a curve, no? Like, maybe another question is, what is the area here? What is this area? Because we can, how can you do it without calculus? Because you would know that if this is a square, it doesn't look like a square, but if it was a square, the area is 1, no? Because it's base times height, or 1 times 1 is 1. So it'll probably be some fraction of that, no? Looking at it, cut it in half. Maybe it'll be a half, a little less than a half. Maybe a little less than a half. All right, so what is this area here? So how can we systematically know what that area is? It answers what is the exact area under the curve. And how do we do this? Most of the time in this one, all the time, this will be, what do you think? Velocity. This is more that it will be velocity, and we want, Whereas here it's not exact. We don't know what f of x is. F of x defined it, and maybe that too, but for what we're doing, it will most of the time be velocity. All right, VLT, and in this case, to find what the area under that curve is, we are going to take the integral. We're going to take the integral of the function. And at the end of the day, basically, we're going to undo everything we did in first semester. So pretty much what it is elementary school, you learn that x plus 2 is some number. So how do you get the x by itself? You do the opposite, which you minus 2, no? And you get an answer. So, and then what was another one that you did something like multiply. 3 times x is 12. What do you do to get the x by itself? The inverse of multiply is divide, no? And so in this, if the derivative is one operation, it's an antiderivative. What the integral is to go back. That's all it is. So we took the derivative and we want to go back to the function that it was previous. All right. All right, let's go. Exploring accumulations of change. Go ahead, take a little bit of time. Go ahead and copy that down. I told you guys it was already open. You should have took the notes down already. So we got this graph again, and it was a problem. I don't know if it was my mistake or whatever, or the Microsoft Word wasn't working when I converted it, but if we don't identify, we don't tell you what exactly this graph represents, it's a big problem, no? So what is this? Is this a position function? Is this a velocity? What is this? And I said, like second semester, most of the time, well, it has to be given, no? It will give, but this graph will have to be velocity for what we're doing second semester. So I'm telling you, it's a velocity function. And we are going to tie what was previously learned and remind you of what you should know already from chapter 5 about when is it that a particle is speeding up, on what interval would it be speeding up, and why would it be speeding up if this is a velocity function. So to answer the question, we were going to say that the particle is speeding up from this letter to that letter, and from this letter to that letter. Because why? Okay. So the particle, when do particles speed up if the velocity is given, or not even if the, well, it's just when is this? When does the particle speed up? When was it?
Velocity and acceleration are in the same direction.
Okay. When velocity and acceleration, velocity. Okay, this is a velocity function. And the velocity is negative here. The velocity is negative, but the acceleration is the slope of that, which is positive. Well, that wouldn't be it. And then we go here, and this is velocity is positive because it's on top. It's positive. Every point here is positive. And the tangent at it is acceleration is positive. Both are matching up. So it has to be B and C. B to C or from B to C. And then this is velocity is positive, but then it's negative acceleration can be. So this is negative velocity, negative acceleration, D to E. They don't match up. Not everybody's taking physics, but another way of looking at it, for those that maybe are taking physics, I'm part of that Facebook group, and then there's a lot of discussions on how people teach it, and some, I don't know if that physics, more calculus-based physics, they teach it this way, that if you are approaching the x-axis, if it's going towards the x, it's kind of like, what is it? Let's see. Is that you're slowing down? You're still you're say this is the position. Where am I going to put it? Say this is a positional. So at A, I'm going backwards, but I'm not going as fast, no? Until where I stop, and then I stop at B, and then I'm going forward, and I'm going faster, until again I stop at not stop at C, but I start. There's a what is that called? Inflection point where I was going faster. Then at C I kind of slow down, and I'm slowing down, and I'm slowing down until D, and then at D I'm gonna go backwards again, and I'm gonna accelerate backwards until I get an inflection point at E. No, an inflection point at E, and I'm slowing down again. So what was that? That when we approach the x-axis, is that we're slowing down, going away, we're accelerating, going towards, we're slowing down, we're going away, something like that, no? But now, okay, let's go. So, when is the particle slowing down? Well, when is it slowing down? From that inflection point going towards the x-axis, isn't it? Would it? Another way of looking at it, wouldn't it? Yes or no? From that inflection point of inflection, going back to the x-axis. Going back to the x-axis, and well, this is going towards it, and this is going towards it, and then towards it. Okay, more to this than that. So we're saying a picture is worth 1,000 words, and on top of that, the more knowledge you have and the more you know, the more questions and more things you could see. What happens here is that this is related to some other function. Say this is a velocity function, and its relation, this is the derivative, the velocity is the derivative of some f function, let's call it, where we said that f is s of t, no? The position. And so, and like I was talking about right here, no? At A, I'm at A right here, no? I'm at A. And then I am slowing down all the way to B. I'm going in a negative direction, accumulating this much, I'm distancing myself from this position here. This is 0. Let's say this is a position of 0. This is my house. And then I go backwards, because but I'm slowing down all the way to B. But I have moved this amount, whatever that amount is. And you know what that amount from there to here is? It is this area. That's what it is. So I have moved backwards that much. And whatever that area is how much distance I've moved from that 0 position. So here it is. The region between the function and the x-axis is called the area under the curve. So between the x-axis and the curve is the accumulation of change. And so the area under the curve gives us the accumulation of change. So that is, we've gone backwards. We're at some B position there where we have 0 velocity, and then we start moving in the positive direction again, which we're accumulating all that, all the way to wherever we stop at D. Then we stop at D, and then we go backwards again. So, from A, let's say here, from A to F, I have started here, Did I end up to the right, or I ended up at the left by the time I got to F? To the left, because this area is bigger than that. So I did this where I went this much, and then I went that much, but then I went a lot more back, so I ended up way back there somewhere. All right, so now let's go back to elementary school, middle school. A car travels 70 miles per hour at a constant velocity. How much distance has the car traveled in 2 hours? Well, going back to just the formula for velocity, When a car travels 70 miles per hour, constant velocity. Velocity is what? Distance over what? Velocity is distance over time. Car travels 70 miles per hour. That is velocity at a constant velocity. How much distance does a car travel in 2 hours? This is time. So I want to get distance. Okay, so how do we get distance by itself? Multiply by time, multiply by time. So that will be distance equals velocity times time. All right, distance is velocity times time. All right, so if distance is velocity times time, plug in, so multiply velocity times time. 70 miles per hour times 2 hours, cancel out the H's, so it'll be 140 miles. Okay, so that's just doing it mathematically. Visually, again, we're looking at a velocity graph. For this second semester, we'll be looking at this velocity graph a lot. So the velocity is constant. A car travels 70 miles per hour at constant velocity. So it's always traveling at 70 miles per hour. Whatever time is, it's always going at 70 miles per hour. It is doing it for 2 hours. The area under the curve is the distance it has covered. 70 times 2 is 140. And you notice that it's on top of the x-axis, so it's positive velocity. All right. We're moving. Let's move. Number 2. A car travels with increasing velocity according to the function v of t equals 10t plus 30 miles an hour. How far will the car travel in the first 3 hours? A car travels in the first 3 hours. So we said distance equals what was it? Velocity times time? Let's see. So distance is going to equal, well, definitely we know time is 3. Well, but how do we do this? Can we just plug in t is 3 and then get that number? 390 times, no? All right, how do we do this? If we graph this, because I'm telling you it's a velocity graph, no? Let's graph it. Isn't this a linear function now? Isn't this like y equals mx plus b? Y equals mx plus b, where 10 is like a slope, and then you got 30 is the y-intercept. So let's graph it. Let's kind of look at it like The area under the curve way of looking at it. So the y-intercept is here, and it goes up 10 over 1. So this is what, 2, is this? Man, how do I have it broken? So this is 1, 2, 3. So it's going to go in 1, it's going to go an extra, another 10, and then, so it's the slope of that. Okay, you guys maybe have better. So it's this area. How can we calculate that area? That's how much it would have traveled. If we because what is this area here? What is this area? Is that 90? 30 times 3 is 90. And then how can we figure out what this area is? Is that base times height divided by 2? That's a triangle, isn't it? So what is that? The height is what? The height is what? Is it 30? The base is 3. 90 divided, is it? So how much is that? 45? So it's 135 miles. So what did I say to do? 3.3. 3. That wouldn't have worked. T is 3. 60, 90. No. Okay. Look, there's this one formula called the formula of a. What's the formula for a? What kind of shape is this? Do you remember this from geometry? What kind of shape is this? The trapezoid. Trapezoid. So this formula for a trapezoid, you need to remember, it was something like this. If you flip it, and then like get it out of the graph. If it wasn't like a trapezoid was that you have this is a base. Would that be the base? This is a base 1, or is this a base? It was something like this. This is height 1, or we call it the base. Height 1. And this is height 2, or the base 1 and base 2. So you add up the bases. So be what? Height 1 plus height 2, if you want to call them that. So add up the height, the bases, times it by the. Is this the height or this the base? If you want to call this the base 1, and this is base 2, then this is the height, I guess. You want to call it, but you get it that it's going to be the ones that are parallel would be called B1 plus B2, and then times the one here. So this is H. I'm calling this B base then 1, base 2, and this is H. And then let's see if that one's going to give me the answer. What's B1 height then? What's B1? 30, and then this is going to be plus what? 60, and then times it by this is what, 3? Then we got it wrong then. Or is that, or yeah, it has to be 30 times 60. Oh, and then divided by 2. What's 30 plus 6, 90 times 3 is what? It's 90 times 3. 270 divided by 2. Alright, so that's how it's going to go. So it is really going to be the area of a trapezoid is just the heights, whatever you want to call them, the ones that are parallel. Add them up, times it by this 1, divided by 2, no? That would give us the answer, yes? H1. Whatever it is, let's see, what do I have? H1, I have them as H. Is H1 plus H2 times the base. I guess that's called, okay. This makes sense. All right. Why? Because let's call this, it's a height, the little height, and the big height, and there's this, the base. You only got one base. All right. So now we got it. And then always divided by 2. So the height of the small plus the height of the big times it, add them up, times it by the base, and then divided by 2. So it's 135 miles. All right, here we go. What is a function defined by integral? So it's getting there where we're connecting second semester with that first semester. What is a function defined by an integral? I'm saying that in second semester, most of the time, the graph given will be some kind of a rate. So f is some velocity, some kind of rate graph. So if f, this particular graph I have here, and I'm using this as an example, if the graph given, if f is a continuous function on AB, which this is a continuous function. It has a line going down, a line going up, and some curve thing. So let's say A is 0. Let's say A is 0, and it's defined all the way from A to B, and B is 7. So if this f function is a continuous function, which it is, it's continuous. It's continuous. Notice that it's not talking about anything about differentiable because it's already a derivative. So it could be twice differentiable and all that kind of stuff. But don't worry about any of that stuff right now. So if f is a continuous function on AB, then the function g of x, which I'm talking about, is the antiderivative of this. See, this is a velocity, VLT. And we want to know what was it before it got derived. So what was the position function? We can call it g of x. See? So this is the antiderivative of this, where it came from. So it will be the area under the curve of this integral. So this is saying that the sum, this is the integral, the sum of the area under the curve from A to B is g of x. Okay, now A, because look, anything moving, you got a car that's moving and you're driving, and all of a sudden you said, hey, you know what, starting now, let's check how much distance we've traveled. So A is like a beginning point. When I was talking about right here, that I'm standing right here, and from there we'll do it. We'll start measuring. So you got to find some beginning point. So in this one, I'm telling you that this A beginning point is at this. It doesn't necessarily have to be here. It could have been here. But let's go with that. But now we start accumulating where this is the variable that accumulates. So this is actually changes. This is more like static. All right? All right, let's go. X is going to go, as you start accumulating from A to B, X will go from A to B. X is greater than or equal to A, less than or equal to B. G of X is continuous on. Okay, now, that G of X graph function that we don't know, the antiderivative of it, does have a connection to this velocity graph in that it has to be continuous on whatever F is continuous on. So if F is continuous on AB, okay, if this continues from 0 to 7, then this g, where it came from, better be also continuous on there. And it has to be differentiable in the inside, not at the endpoints. So it'll be g, where it came from again, the antiderivative function, would have to be differentiable on a, b. So not at the endpoints again. We don't, yeah. So there has to definitely be differentiable within 0 to 7. Okay. And therefore, what I've just said is that g is the antiderivative of this function, where I could just say now that if I take the derivative of this, look, if I take the derivative of this thing, d dx or whatever, d dx of this thing, then I'm going to get g prime of x will equal to this function, where these are variables. T's are for this velocity function, but then we just plug in this x in for t. In reality, it's just more complicated what I'm saying. It's just that f is the derivative of g. G prime of x will be, g prime of x is this f. All right, so now let's start playing with accumulating and getting positions off of this. So here's the problem number 3. Let g of x equal the integral from a to x of f of t dt, where f is this function here. Evaluate g of x for x equals 0, 1, 2, 3, 4, 5, and 6. So g of 0. G of 0 will be the area, the sum of the area under the curve. And I said, no, at time equal to 0, that's when we start measuring or measuring how much we've changed in this distance, the distance changed. So at time equal to 0, I'm still here. At time equal to 0, I have not moved at all. We're just starting, no? So we're starting, so time equal to 0, this is 0, and then this x value, that's what this is. This is that x is 0, and we have not moved f of t dt, f of t. So I'm here and I have not moved. There's no area whatsoever. I'm just there. So this is 0. There's no area under the curve there. Now we start measuring, and let's go to what would be the distance traveled or the area accumulated under the curve, g of 1. So how much area have we accumulated from 0 to 1? So it's saying, what's the area under the curve from 0 to 1? What's this area? And it's got to be positive, because it is on top of the x-axis. What's this area? 1/2. That is 1/2. 1/2. That's all it is. So what have I done? What have I done? So I'm here again. I'm starting at 0, 0. Then I went half of whatever it is that I'm talking about. Is it whatever it is? A mile, half a mile. I went forward. And then I abruptly, I went stop, I went backwards. So G of 2, and it's talking about from starting from that 0. Then I went forward, then I'm gonna go backwards. So what do you guys think the answer is gonna be there? What's the answer to that? Huh?
Zero.
Zero. Zero. Zero. Why? Because look, at zero, we're here. I'm here, you know. I'm here. I went forward a mile, half a mile. And I went back half a mile. I'm back to zero. G of 3. What do you guys think G of 3 is?
Negative 0.5.
Yeah. Because I'm at zero, then I'm back here. So I'm back. So from that, I'm back at negative a half. G of 4. What's going to be G of 4?
0.
0. I'm back. Go back to that position where I started. G of 5. What's G of 5? Wasn't that what we just did? No, that one. Because this doesn't. Okay. Okay. So this canceled with this. I'm gonna look at this canceled. This canceled with this. So I just need to know what this area is. What was it? Was it H1? What's H1? This is 1, no, isn't it? 1. And then this is what? And then times about what? Divided by? So what's that? 3 halves, 1.5? Yeah, because we already said this comes with this comes with that, which we already did that, no? We just want to know this area, no? G of 6. What's G of 6? Well, one way to look at it, that up to this point, where we're at positive 1.5 miles or whatever, no? Up to whatever has happened here, it's already 1.5, yes or no? And I'm going to add, because it's positive, I'm going to add this right here to it, no? Which is going to be what? The H1 plus H2 quantity times it by B divided by 2. Which H1 is what? H1 is 2 plus what? 3? 2 plus 3? The quantity, hold on. It is, what am I doing? Let me erase. I just wanna. I could easily erase this better. Look, we want to know what this is, and we figured out that it was what H1 is 2 plus what 3 times by 1 over 2. So it's good. What's that?
5 over.
Which is 2.5, isn't it? Yes. 2.5 plus 1.5 is what? 4. And now we come into this problem about what the heck is this? Because it's a curve. You could estimate that what it could be. I don't know. I could estimate it would be an estimate that's bad. I would say like this is just kind of using that this is definitely what? What is this? The whole thing that I'm doing. This rectangle is 3, isn't it? 3 times 1 is 3, yes? And then I want this. It's a little more than 1. Wait, a little more than 1. It's a little more. It's more than 1.5 at least. If I say it's this half, it's half this, half that. It's still a little more than 1.5. It probably is 2. Whatever it is, okay. It's like 2 maybe. We could estimate that, but don't worry about that right now. That's it. That would be it for today.